In chapter 2, we are going to be using some of the fundamentals of matrix theory and applications of matrices. So I want to start by showing you some of the mathematical conventions we use to represent matrices. So in this first row here, we've got the 3 different ways to represent the same matrix. We can use the uppercase letter. In this case, we use A. Other common letters are B, C, D, etc. Matrix can be represented the second way here as a representative element enclosed in brackets. So in this case, A with the subscripts I and J that correspond with the dimensions or locations for each element inside the matrix. And then the third way is as a rectangular array of numbers. So in our rectangular array here, we have m rows and n columns, and each entry in the matrix is represented by its position, rows first, column second, in the subscript. So over here, the entry A to N is in the second row and the nth column. So we have some operations with matrices that we're going to be practicing in this section. Before that, we want to go over some of the properties and definitions. So the definition of equality of matrices is here in the first box. So two matrices A, and you can write it as capital A or in the brackets, and B are equal if and only if they have the same dimensions or order. In that case, that means the same number of rows and number of columns, the dimensions. Typically, we say m by n, where m is rows and n is columns, the numbers of each of those. And then if each individual entry in the same position equals. So for example, whatever number I have in A22 here would have to be the same entry in B location 22, second row, second column in matrix B. And that has to be true for all of the rows and all of the columns. So every entry has to match to say that two matrices are equal. All right, there's some logic introduced here. So if we say P if Q, sometimes written Q implies P, going in that kind of backwards direction. You can think about an example of that as saying it is cloudy if it is raining. And an example of Q only if P, often written if Q then P, is also written Q implies P in the forwards directions. We can think about an example of that as saying it is raining only if it is cloudy. And then the third kind of logic term that we use very often in math is this if and only if statement. Sometimes for short, we say IFF, like right here. So if we say R if and only if S, that's shorthand for saying R if and only if S is true. And since they both depend on each other, we write it with this arrow going two directions. So that means that R is equivalent to S. Like if one is true, then the other must also be true. So in this example, we're going to take a look at adding and subtracting matrices. So to add or subtract two matrices, A and B that have the same dimension, you add or subtract the corresponding entries that are in the same place. So in order to add and subtract matrices, it's important that they have the same dimension. We'll do a little test here in Sympy to see what happens, what kind of error we get if we try to subtract matrices with different dimensions. So the second note here says the sum and difference of two matrices with different dimensions is undefined. So you just get an error message if you're trying to do it in technology, and you couldn't do it by hand because there aren't enough entries matching in the same position. And then if you want to multiply a matrix by a scalar, constant number, you can just multiply each entry by that scalar. So let's take a look at some examples here in my next slide. So I've constructed matrices A and B here for us to work with, and a third matrix D. A is a 2 by 3 matrix because it has 2 rows and 3 columns. B is a 2 by 3 matrix because it also has 2 rows and 3 columns. And D is a 2 by 2 matrix because it has 2 rows and 2 columns. So let's go ahead and calculate A plus B. So I'm going to take each entry in A and add it to the corresponding entry in B. So the first entry in our new resultant matrix is going to be 1 plus 1. The second entry in row 1, column 2 is going to be 2 plus negative 4, or just 2 minus 4. The third entry in row 1, entry 3, is going to be 4 plus 3. And then if I come to the second row, negative 3 plus negative 1, or negative 3 minus 1. Then we've got 0 plus 3, and negative 1 plus 2. So if I simplify here, those values should be 2, negative 2, 7, negative 4, 3, and it looks like just 1, a positive 1 here. I'll get my eraser and erase my sign there. All right, looks good. So we calculate A minus B similarly. I'll change colors here. So A minus B is going to be 1 minus 1. A minus B is 1 minus 1 in the first entry. Then in the first row, second entry, we're going to have 2 minus negative 4, so this is going to become 2 plus 4. In the first row, third entry, we're going to have 4 plus 3. Oh, sorry, 4 minus 3. Then in the second row, first entry, we're going to have negative 3 minus negative 1, so it'll be negative 3 plus 1. And then we're going to have 0 minus 3 and negative 1 minus 2. So these values work out to be 0, 6, 1 in the top row. And then in the bottom row, we should get negative 2, negative 3, and another negative 3. Okay, the third question here asks us to find A plus D. So is that even possible? Well, A is a 2 by 3 matrix, and D is a 2 by 2 matrix. So I'll put a note here that we cannot calculate A plus D, since A is a 3 by 2 matrix. And D is a 2 by 2 matrix. So in order to add matrices, they must have the same dimensions. All right, our last calculation is to calculate 4 times matrix A. So we are going to multiply 4 by our matrix A, 1, negative 3, 2, 0, and 4, negative 1. And so to do that, we take each entry and just multiply by 4. So we're going to get 4, 8, 16, and then in the second row, negative 12, 0, and negative 4. So you saw here in this example how easy it was for me to make a simple arithmetic mistake, which would throw off all of my calculations. So a much more efficient and accurate way to do matrix calculations is to use technology. So I'm going to head over to Sympy and verify our calculations there. So I'm going to Sympy Live. So that is live.sympy.org. And this is the regular Python shell running the symbolic Python. So those commands are already run for us. So I'm going to go ahead and enter matrix A. I'm going to say, oh, scroll back up. Make sure I'm here on the command prompt. So I'm going to say A equals matrix. And then in parentheses, I put my matrix function. I'm going to do double brackets and enter the first row. So A is 1, 2, 4 in the first row. And -3, 0, -1 in the second row. I'm going to close it off with double brackets and parentheses. And then just to double check I've entered it correctly, I type A and hit enter. And there is my matrix. All right, I'm going to enter a matrices B and D as well. When you type the matrix function, you have to use a capital M. And for really small matrix calculations like A and B, since they're 2x3 matrices, you can weigh out, is it better just to do the calculations by hand in terms of the time spent typing them into a computer system. So I'm just verifying here by typing B that my matrix entry is the match for what matrix B was, and it looks like I've typed it correctly. And then I'm going to enter matrix D. Matrix D is the 2x2 matrix, so we know that it won't add or subtract with a 2x3 matrix. But we're going to see what kind of error we see from the computer. All right, so the first calculation we want to check is A plus B, and so we can type just so simply A plus B and hit enter. And voila, that matches our calculations that we did by hand. We can check A minus B, and we get another match that verifies our calculations that we did by hand. So we can see technology, once we enter the matrices, can quickly calculate for us and save us arithmetic errors like I might make doing calculations by hand, or missing negative signs that are also really easy to do. If we try to add A plus D, we get a result that this is undefined. Notice that last row of my error result says shape error, matrix size mismatch. So it's saying you've got a 2x3 matrix and a 2x2 matrix, and so you can't add those up. You wouldn't have the right entries that match each other. And then if I want to multiply matrix A by 4, I can do 4 times A. You got to make sure you have the multiplication key in there in the Sympy program. And then it multiplies all of my entries by this scalar or number value 4. So we can see we can use technology to verify our calculations that we've done by hand.